In this video, I will demonstrate how to solve polynomial inequalities. A polynomial inequality is an inequality of the form f of x is greater than 0, f of x is less than 0, f of x is greater than or equal to 0, or f of x is less than or equal to 0, where f of x is a polynomial function. Some examples of polynomial inequalities are x squared minus x minus 6 is greater than 0, 2x cubed minus 18x is less than or equal to 0, x to the fourth minus 13x squared plus 36 is greater than or equal to 0. Notice that the side opposite of 0 is a polynomial expression. It can be a quadratic, a cubic, a quartic, or any combination of those types of things that we've studied before. Recall that zeros of a polynomial function are the values of x such that f of x is equal to 0. Whenever we solve an equation of that form, we're trying to find what value of x makes the output 0. Recall that those points correspond to the x-intercepts of a graph. Right, graphically, a point on the x-axis represents the ordered pair x0, so that is the x value that produces 0 as the output. At all other values of x, f of x will be either positive or negative. That is greater than 0 or less than 0. Does that make sense? Because a number can be only one of three things. It can either be a positive number, 0, or negative. And so if we know where it's equal to 0 at every other value of x, that function value will be positive or negative. And we can see this graphically. I have drawn for you the graph of f of x equals x squared minus x minus 6. Recall this is a parabola that opens up because the coefficient of x squared is 1, which is positive. Note that the zeros of the function correspond to the x-intercepts of the graph, which we just talked about. And so those x-intercepts are negative 2, 0, and 3, 0. Before and after a 0, the graph alternates between being above and below the x-axis. Can you see that? To the left of the negative 2, 0, the graph is above the x-axis. To the right of it, it is below. And then before our other 0 of 3, 0, the graph is below the x-axis, before that, and then it's above. Right, so as it crosses through the x-axis, it changes from positive to negative. And do you remember how we looked at that in the intermediate value theorem? We talked about with a polynomial function, when there's a sign change between a positive and negative function value, we know there's a 0 between those values, so this is kind of being confirmed here as well. But this is where the function values are either positive or negative. And this is one reason, again, I love math, because if you look at the algebraic expression, that equation or function, you can certainly plug in values to determine where it's positive or negative, but if you look at the graph of it, it gives us a visual representation of every single ordered pair on that graph. And so we know just from looking where the sign changes from positive to negative and what values make it 0 and so on. But this is the great thing. So I want you to kind of understand this. So I've drawn like a number line below this graph. Think about that as just kind of the x number line. And on this number line, I see that there were two values of x negative 2 and 3 that made the function value 0. So this is telling me what the sign of f of x is. And then to the left of negative 2, because it's above the x-axis, every function value on there is going to be positive. In fact, like if I plug in negative 3, do you see how it crosses at 6? Negative 3, 6. I don't have to identify every single point. The fact is, because it's above the x-axis, the y values are positive, right? Y is positive in quadrants 1 and 2. Y is negative in quadrants 3 and 4. And so because the graph to the left of negative 2 lies in quadrant 2, I know the function values are positive. Between the negative 2 and 3, the graph lies below the x-axis, so I know the function values are negative. Again, I could confirm if I plug in 0, I get 0, negative 6. So notice that the y value is negative for that particular x value. At 2, it's negative 4. Right, again, the y value is negative, but I know that just because it is below the x-axis also. And then to the right of 3, the graph is above the x-axis, which makes the y values positive. But if I identify a specific point, like 4, 6, I can see that the y value is positive there. So algebraically, we can determine the sign of a function by using test points. We first find the zeros of the function by solving the equation f of x equals 0. And in the example that we just had, that function was x squared minus x minus 6. We'll set it equal to 0 and solve by factoring the factors of 6, whose difference is 1, are 3 and 2. We know the signs are different because of the last sign. And the negative in the middle tells us the larger factor needs to be negative. So we get that the zeros are 3 and negative 2, which we just saw that on the graph. Then we will determine the sign of the polynomial in intervals around the zeros by testing a specific value in each inequality as shown. So notice what we said. Our zeros were negative 2 and 3. So the intervals around these are from negative infinity to negative 2. Some people like to identify those as like interval A. Between negative 2 and 3, interval B. And to the right of 3, which is from 3 to infinity, we'll call that interval C. And so we're just trying to find a value, because remember what we just said. It's either going to be all above or all below in one of those regions. So we just need to test one number in that region to determine it. And this is if you don't want to use a graph. I'll show you how to use a graph as we go on. But a number between negative infinity and negative 2, let's use negative 3. There's infinitely many to choose from. So our function was f of x equals x squared minus x minus 6. So our function value, if we substitute negative 3 for x, we get negative 3 squared minus negative 3 minus 6. And that's what? 9 plus 3 minus 6. 12 minus 6 or 6. So the sign of f of x is positive. In the interval between negative 2 and 3, we're going to plug in 0. Any number would do, but if 0 lies in the interval, that's the easiest number to test. 0 squared minus 0 minus 6 is just negative 6. So the sign of f of x is negative in that interval. And then from 3 to infinity, we'll plug in 4. 4 squared minus 4 minus 6. What is that? 16. Minus 6 is 10. Minus 4 is 6. So the function is positive on that interval. So using that graph in the table that we just created, we see that the function, that is f of x, is negative on the interval between -2 and 3. F of x is greater than 0 on the interval from -infinity to -2, union 3 to infinity. So there we say the output of the function is positive at x values less than -2 or greater than 3. F of x is less than or equal to 0 on the interval from -2 to 3, including those endpoints. So notice the difference between the first one and the third one. In the first one we had strictly less than, so we cannot include where it's equal to 0. But on the third example, we can include where it is equal to 0. So the output of the function is negative or 0 at x values between and including -2 and 3. And then f of x is greater than or equal to 0 on the interval from -infinity to -2 bracket, union bracket 3 to infinity. This means the output of the function is positive or 0 at x values less than or equal to -2 or greater than or equal to 3. So when we're trying to solve an inequality, what we're trying to determine is what interval or intervals of x yield a positive output, a negative output. So we'll see how we can do that. The steps to solve a polynomial inequality is we first rewrite the inequality so that it is in the form f of x greater than 0, f of x less than 0, f of x greater than or equal to 0, or f of x less than or equal to 0. That is, we set one side of the inequality to 0. Then we find the zeros of the function by solving the equation f of x equals 0. This is a critical step. These zeros are also called boundary numbers. And so we always find those boundary numbers by solving the associated equation. Then we want to determine the sign of f of x at intervals around the zeros by evaluating the function at a specific point in each interval, or by using the graph of f of x. Then we want to determine which intervals satisfy the inequality, that is, which interval gave us a true inequality when we replaced that value of x with that specific number. Then we need to determine if the zeros are included in the solution set. So they will be included if we have a less than or equal to or greater than or equal to. And that means that we're going to use brackets. If they're strictly less than or strictly greater than, then the endpoints or zeros are excluded. And we use parentheses. Then lastly, we will write the solution set of the inequality in interval notation. An example is x squared plus 4x minus 12 is greater than 0. We already have one side equal to 0. So then we set x squared plus 4x minus 12 equal to 0. We can factor this by finding the factors of 12 whose difference is 4. And those are 6 and 2. We need different signs with the larger one being positive. So the two zeros are found by setting x plus 6 equal to 0 or x minus 2 equal to 0, giving us x equals negative 6 or x equals 2. And so what we want to do is place those numbers on a number line to determine what intervals we need to test. So we need to test from negative infinity to negative 6, between negative 6 and 2, and then from 2 to infinity. And again, if you want to call those regions A, B, and C, you can certainly do that. So we need a test point from each of those intervals. To the left of negative 6, we have negative 7. Between negative 6 and 2, we will use 0. Again, the easiest one to use if we can. To the right of 2, we'll use 3. And so now we'll substitute. If I replace x with negative 7, I'm replacing the variable in the original inequality. So negative 7 squared plus 4 times negative 7 minus 12. And what I want to determine, is that greater than or 0? Well, that's 49 minus 28 minus 12. Or 49 minus 40, which is 9, which is greater than 0. And so that results in a true statement. In my second interval, I'll test at 0. So 0 squared plus 4 times 0 minus 12, is that greater than 0? No, that would be negative 12, which is not greater than 0. So that resulting inequality is false. If we replace x with 3, we get 3 squared plus 4 times 3 minus 12. Is that greater than 0? That's 9 plus 12 minus 12, which is 9, which is greater than 0, so that is true. So the intervals that satisfy the inequality are included in our solution set, so that tells us everything to the left of negative 6 or to the right of 2. And we do not include those endpoints, so we will have a strict parentheses at those particular points. Our solution set is from negative infinity to negative 6, union 2 to infinity. Now, how could we use the graph to figure this out? And in fact, you don't even really have to go to your graphing calculator. If you remember how the graph looks just by using the end behavior of the graph, in this case it's a parabola that we know opens up and it has zeros at negative 6 and 2. So the only way that can happen is if it is up above the negative 6 and then goes down and then comes back up, right? If you just know a rough sketch. Also, a even degree polynomial with a positive leading coefficient has both ends up, right? The end behavior is up at each ends. So we know that to the left of negative 6, that graph is above the x-axis. Between negative 6 and 2, it's below. And to the right of 2, it's above. So that means in the intervals to the left of negative 6 and to the right of 2, I'm going to have positive function values there, which was confirmed by plugging in a point. And so that's another way that you can use the graph to determine the solution of this inequality. You'll always have to go through and find your zeros. But after you do that, you can either test points or use the graph. Now we have a negative 2x cubed minus 6x squared plus 8x plus 24 is less than or equal to 0. In this case, we have the inequality set equal to 0, so we're just going to solve this associated equation. To solve this 4-term polynomial, we will use grouping, Pairing together the first two, there's a negative 2x squared common. Factoring that out leaves an x plus 3. Between 8x plus 24, there's an 8 common. That leaves an x plus 3 equals 0. So we see an x plus 3 is common, and we have a negative 2x squared plus 8 equals 0. We could factor this further, but really our goal is to solve for the 0. So at this point I'm just going to set x plus 3 equal to 0, or negative 2x squared plus 8 equals 0. So we get one 0 is negative 3. Then the other 0 is negative 2x squared equals negative 8. Right, we're going to solve using the square root property. We divide by negative 2. We get that x squared equals 4. So therefore x is plus or minus the square root of 4, which is plus or minus 2. We can place these solutions, these zeros, or also called boundary numbers, on the number line. Place them in order from smallest to largest, so negative 3, negative 2, and 2. And from that, notice that we have 4 regions to test. I'll label these A, B, C, and D. So region A is to the left of negative 3, so negative infinity to negative 3. Region B is between negative 3 and negative 2. Region C is between negative 2 and 2. And region D is 2 to infinity. What I could do in this particular situation is I could identify a test value or a test point in each interval. Let's say in the first interval, maybe negative 4. The second interval is going to be trickier because it's between two integers, consecutive integers, so we need to use like negative 2.5. Between negative 2 and 2, we could use 0, and to the right of 2, we could use 3. So what we would have to do then is take these values and substitute into the equation. Now you could use your calculator. If on the calculator you input the side opposite from 0 into your equation editor for y, and then you could look at the table and figure out what the output is at each of those. But I'm going to do something different in this problem. Instead of replacing x with each of those numbers and solving that expression, what I want to do is think about the end behavior of this function. This is an odd degree function, and it has a negative leading coefficient. So without even picking up my calculator, I know the end behavior. I know it's going to be up to the left and down to the right. So remember graphically what that would mean. It's going to start above, and then it's going to come down through this 0. So it's got to come down, but then it's got to cross the x-axis again. So it's going to come up again through that negative 2. Then it's got to come back down to go through the x-axis again at 2, but then it stays down. So my graph is not drawn to scale really, but understand I can get what the basic shape of that function has to look like. So to the left of negative 3, my function is above the x-axis. What do we know above the x-axis? The function values are positive, right? F of x is positive there. Between negative 3 and negative 2, it's below the x-axis. F of x is negative there. Between negative 2 and 2, it's above. So the function values are positive. And to the right of 2, it is below, and the function values are negative. Again, I could plug in these particular points and figure that out, but the graph helps me see that so quickly. And then I wanted to find where the function was less than or equal to 0. So that's where it's negative or 0. Well, negative means where the graph is below the x-axis. So it is below the x-axis between the negative 3 and negative 2 and to the right of 2. Now I can also include my zeros because it's less than or equal to. So my solution set would be from -3 to -2, union 2 to infinity. We can also graph the solution set. If I just shade those numbers between -3 and -2, and to the right of 2 using brackets on the zeros, I could get a graphical solution. So let me know if you have any questions on this concept.